Today's topic is center of mass, linear momentum, and collision. Now, you may have a system which may consist of different particles, bodies scattered around all over the place. For example, this is particle P1, this is particle P2. And you may like to know if you have a number of particles, P1, P2, P3, all these things. You may like to know where all these particles seems to be concentrated, where the weights of these particles seems to be concentrated. At that point where it appears that all the weights of these particles are concentrated is called center of mass. The particles don't exist at the center of mass, but it appears that if you replace this particle, and all other things with total mass at this center of mass, then it is an equivalence, right? Okay. Now, we can define center of mass as, it's a vector because it's a position vector, is equal to, what we do is we take all particles with their respective masses and their coordinates, the distance from a fixed coordinate. For example, this may be R1, this may be R2, right? So if we sum up all position vectors, multiply by their respective weights, and sum all of them, what you get is center of mass, position of center of mass. Now, center of mass can be measured from any frame, any inertial frame. It's not necessary that your origin should be here. Your origin could be anywhere else also. It doesn't matter. The position of center of mass will still remain same by this formula. Okay. Now, this is with respect to position vector Ri. Now, it may not be very easy to find this position vector Ri in this form, but what you can do is you can break it into ijk components. So what we can say is that x component of this position vector can be calculated as total mass of the body, and then you sum the I components with respect and mass multiplied by its x component. Okay. Similarly, y component of center of mass will be exactly same way. And if you have a z component will be similar. Okay. Now let's try to find the center of mass of a semicircular disk. This is the diagram of this semicircular disk. This light gray portion is a semicircular disk. What we do is we make a small annular ring, which is a dark gray color here. Do the analysis on this ring and then extend the treatment from R is equal to 0 to R is equal to total R. Okay. Now, this is a slice of what you see here. This is the portion of the disk which is at a distance r, making a small angle theta within itself, and the width of this thing will be r d theta. Okay. So the weight of this disk will be what? The weight of the disk is small dm. R d theta is the width of this slice, and this theta is dr long. Dr is this dimension. So the total weight will be area of this small portion into its surface density, which is this r d theta into dr into rho. This is the total, this is the mass of the small portion that we had taken out. Okay, right? Now what we do is we first do the treatment on this ring and then integrate this ring over the complete area. So if we take dm as the mass of this annular disk, which will be equal to what is the area of what will be the mass of this disk? It will be the area of this disk, which is 2 pi r by 2, because it's semicircular disk, into dr. Dr is the thickness of this disk, okay, and rho is the surface density. So what you get is rho 2 pi r dr as the small mass of this semicircular disk. Okay, and if we integrate, and what will be our center of mass? Center of mass will be, as we mentioned again, summation of all radial vectors into its mass, integrate over the whole, all the particles. Okay. Now we've seen this, that rho into now consider this, we are taking this area as the portion area in question. Now what is the x coordinate of this? X coordinate of this area will be r cos theta, where r is the radius of this particular piece that we're talking about, and theta is the angle which this piece makes with the center. So this is the position vector of our small piece in consideration, and this is the small mass dm that we calculated earlier as the mass. Now if we integrate it over complete theta, what we'll get is the center of mass due to this particular ring only. So if we integrate it over theta, what you get is this. Why is it so? It is so because if you see, all the particles here are equally are symmetric about this axis. if I take a small slice here, its x-axis coordinate will be this, but I have a similar slice opposite to it also here, this one, whose coordinates will be negative. Now, if I integrate all the positive and negative coordinates in x direction, the sum will be 0. Okay, all right. So what we can say that center of I component of center of mass of a semicircular disk will be 0. Okay, all right. Let's take the y component. When we take y component, the distance of this slice that we were talking about will become r sin theta, this much. Okay. So these equations remain same except that r cos theta gets replaced by r sin theta. Everything else remains same. And if we simplify, this becomes this much. This is if we integrate it over 0 to 180 degrees, this theta if we integrate over 0 to 180, because our theta starts from here and goes all the way up to 180 degrees. When we do this, our integration over theta becomes this much. Okay. Now what remains is this simplifies to this equation. Now we integrate this equation with respect to r going from 0 to r. Why? Because we had considered this as a small ring with radius small r. But if we have to find the center of mass for the whole disk, then we have to integrate this r going from 0 to complete r. And that's what we have done here. This integration goes from r is equal to 0 to r is equal to r, which is this thing, and after simplification we get this. Now so our center of mass is contributed only because of y component. We have seen that because of y component, this contribution was 0. So the center of mass of a semicircular disk is 4r by 3 pi. Okay. Now, and as an example, let's take a square whose side is a, and at the corner of each we place different weights. For example, we put weight m1 here, 2m here, 3m here, and 4m here. And let's take the coordinates. Coordinate of this will be 0, 0. This will be a0. This will be, and this will be 0a. Okay, right. Now what we do is we find the our objective is to find the center of mass of this system of particles. The easiest way to do is take component wise center of mass. So center of mass, x coordinate of the center of mass will be summing xi onto whatever. So this will be total mass is 4 plus 3, 7, 7 and 2, 9, 9 and 1, 8, 10. 0. If you take distance from x-axis, this will be 0. Distance of this from x-axis is 2m. Similarly, this will be same distance. And the fourth one will be 0. So this becomes this distance is A. So this becomes 5 MA over this is equal to. Similarly, if we do treatment for Y component of center of mass will be this will be total mass is 10. For the first component, they are on x-axis, so their Y component is 0. For this one, Y component is A. For this also, Y component is A. This becomes okay. So we can say that center of mass can be defined as x coordinate plus the y coordinate. Now, if we have a z component can be treated exactly like this. Okay. There's a small correction. This is 10 m. This is the total weight of the system. Similarly, this is 10 m. Total weight of the system. Earlier, we have seen how to calculate center of mass of a system of particles. And what we had assumed that all particles were at rest. Now, what happens if they are moving? Now, there are different cases. Like what? Case 1. If center of mass is at rest and no external force is applied, then center of mass will remain at rest irrespective of the position or movement of the particles. Second phenomena is if center of mass is moving with constant velocity, and no external force is applied, then center of mass will keep moving with same velocity. This case was when center of mass was at rest. This is the case when the center of mass is moving, but there is no external force. Now let us take a third case, that center of mass neither at rest nor it is moving with a constant velocity. It is moving with an acceleration. In that case, what happens is acceleration of center of mass multiplied by total weight is equal to the sum of individual mass into acceleration. Center of mass, if it has an acceleration, it can be calculated as sum of individual particles acceleration. Let's assume we have a particle which is moving with a velocity v. Its mass is m. Then we defined a term called momentum, which is equal to its mass times velocity. Momentum is a vector because it gets multiplied by velocity. Velocity has a direction. Okay. Now, what will be its kinetic energy? We all know kinetic energy will be half mv square by 2. Now here, it doesn't matter which direction v is going because it's a scalar quantity, right? Now, we know, let us say this body or this mass m, which is traveling in direction v, hits another particle. Let's say this was m1, this was m2, velocity was v1. It hits another particle whose mass is this thing, and which was also moving with another velocity v2. All right. Then what happens that this particle is going to collide with this. Okay. So what we have is collision. Now what happens during collision? We have two types of collisions, two categories of collision. One is perfectly elastic, and second is inelastic. Now during perfectly elastic collision, two things are maintained. One is linear momentum is maintained. Second, linear momentum is total of both the particles, both the bodies put together. And here again same, total kinetic energy of the system preserved, is conserved. Now, if we write it in terms of equations, what will happen is, if there was a mass m1 which was traveling with velocity v1, it hits another body whose mass was m2, was traveling with velocity 2. This is their initial momentum, and let us say v1 dash is the final velocity of m1. Similarly, v2 dash is the final velocity of m2. So this is as per this law, that is linear momentum. This was initial before collision, this is after collision. It is maintained. What happens to kinetic energy? Kinetic energy will be this is the kinetic energy before collision, and this is equal to, and this is the kinetic energy after collision. This is kinetic energy before collision. This is kinetic energy after collision. So this is conserved as per the second law. Okay. Now let us say if we call this as equation 1 and this is as equation 2, if we solve equation 1 and 2, it will lead us to a very nice phenomena called v1 minus v2 is equal to what is this? Difference in velocity of two particles, and this we call as velocity of approach, and this is final difference in final velocities, and we call it as velocity of separation. The velocity of approach mathematically is written like this, and so is velocity of separation mathematically is written like this. But from understanding point of view, what does velocity of approach means? Velocity of approach is velocity with which the distance between the two bodies is decreasing, wherein velocity of separation, it is the velocity with which the separation between m1 and m2 is increasing. Okay, just for the sake of understanding. Now, what happens in inelastic collision? Okay, our linear momentum is maintained. But what happens to our kinetic energy? Kinetic energy is not maintained, not conserved. So what happens to kinetic energy? Now, during inelastic collision, some of the kinetic energy is lost in terms of heat or friction or whatever. So kinetic energy is not conserved. Now we define a term called coefficient of restitution. In a layman's term, okay, first let me give you the value range. We defined it by a letter called E. this is always less than 1 and it is always greater than 0. Lies between 0 and 1. What it means is as E approaches 1, the collision tries to come close to 1 means close to elastic collision. And if it approaches 0 means it is approaching inelastic collision. Okay. So we can also define coefficient of restitution as velocity of separation after collision as E times velocity of approach before collision. Right? If E is 1, then velocity of separation becomes equal to velocity of approach, which is the case of perfectly elastic collision. As it keeps decreasing, it keeps moving toward more and more inelastic collision. But mathematically, E can be defined as, in terms of velocity of separation and approach, E is defined like this. Okay. Now we define another term called impulse. Let's say there is a particle which has got its momentum, initial momentum as pi, and what we do is we apply some force for a very short while, so that's so that its momentum changes to ef. Now what happens is there is a change in momentum. Okay, and this we can take it as some small change over momentum, which is going from initial to P final. All right. This also we can say as T going from sometime T1 to T2. Okay. Now what is this term? This is rate of change of momentum. And we know what is rate of change of momentum is nothing but force. So this whole term becomes this one, which means the change in momentum over a small time from T1 to T2 is equal to integration of force applied over a small time integrated over time is equal to T1 to T2. Now, this term we call as impulse. Impulse is force applied for a very short duration. What could be the example? The example could be you are hitting something with a hammer. You you strike for a very short while. So this time is very short. All right.